Okay, this is going to be an energy problem, and it's going to involve figuring out how much money it costs to boil a pot of water. Here, let's do this in black. Here is a pot of water, and the water is how much water do we have? Well, 4 liters worth of water. And the initial temperature of the water is going to be 6 degrees Celsius. And our objective is to get it to 100 degrees Celsius. Okay? Now, of course, usually when you boil water, you don't just get it to boiling temperature and then say we're done. But we just want to know how much it's going to cost us to get it to that temperature. Now, we need a few other pieces of information. We need the specific heat capacity of water, which is 4180 joules per kilogram Kelvin. We also need another piece of information, which is the price of electricity. The price of electricity, we will say, is 9 cents per kilowatt hour. That's what electricity is usually sold by the kilowatt hour. So it's pretty clear that in order to solve this problem, we're going to have to say Q equals mc delta T. We're going to have to use this equation to find out how much energy is consumed. But wait, I'm going to add another little tidbit into this. And this is kind of interesting. You see, how do you boil water? Let's assume that we have either electric or gas stove. I'm just going to draw, just for simplicity's sake, here I'll draw an electric coil. Now think about this for a second. Does all of the electricity energy which gets transferred into heat, does that go into the water? Now be careful here in terms of what I'm saying, because we need to make a really good understanding of where this energy is coming from. Let's draw a little line here, and we'll say this is electricity. Okay, this is the stove. Okay, now this is heat that comes out. But this now is the water. This process, going from electricity to heat, we'll assume is 100% efficient. In other words, we will assume that for a given amount of electricity that goes into the oven, that much heat has to be created. By the way, let me back up a little bit in this problem. Obviously, if we're using electricity, it's not going to be a burner. It's not going to be a gas stove. Okay? But what is the efficiency going from the input heat into the useful heat into the water? This is very interesting because I'm going to say that this is 70% efficient. Okay? And we can really pretty much ignore this one. We could just say ignore, because this doesn't come into the problem at all, but this one does. Now, what does this 70% represent? Let's discuss that for a moment. What I'm talking about here is, let's draw the picture again here, and we have the coil, the heating element, which heats up. Now, there's heat, let's make it in red, that leaves this thing and that goes up. Well, some of it definitely does make it into the water, but let's say only 70% makes it into the water, and 30% is basically used to heat up your kitchen. Okay? After all, Your stove is warm after boiling water. The air around the stove is warm. So we'll say it has an efficiency of 70%. So what I'm talking about here is the input energy is all of the energy that comes off the stove element. Okay, and the output energy, the useful output energy, is the percentage of that heat that actually makes it into the water. I hope that's clear. Now, let's continue with the problem. And let's say that the mass obviously is 4 liters. Now, 4 liters is equivalent to 4 kilos for water. So if we say Q equals mc delta T, M is going to, oops, we said 4, not 5, 4 kilos times C, 4180 joules per kilogram Kelvin, multiplied by, now the interesting thing here we go. You notice delta T, I gave you Ti and Tf. Let's convert that to Kelvin and see if we actually need to do the conversion. Now what's the equation? Kelvin equals C plus 273, right? So therefore, if I was to convert 6 degrees, which was the original, plus 273, that's going to give me 279. And if I take the final temperature, 100 plus 273, that's going to give me 373. Now, if I actually then subtract 373 minus 279, that's going to give me 94. But you see, that's exactly the same as what it would be if I just used Celsius. If I went 100 minus 6, I'd still get 94. So what's interesting to note is you don't need to actually do the conversion to Kelvin when you're doing the subtraction. It's good enough to say 94. Now listen, what are the units on this? Well, we have to use Kelvin. Why do we have to use Kelvin? Because it has to cancel with that unit there. But understand that the delta is going to give you 94 Kelvin and 94 Celsius. For a delta, they're the same. Okay? Because of this equation. Okay? So what's the bottom line? Bottom line is save yourself a little bit of work. All you need to do is 100 minus 6, and you can just use 94 Kelvin then. Yeah, the difference is always going to be the same. Okay? And that's what we're dealing with because we're not dealing with a temperature by itself. If this was T, we would definitely have to do the conversion to Kelvin. But because it's delta T is the same for Celsius and for Kelvin. We don't need to make the conversion. Now, what's this all going to give us? Well, we get out our calculator, trusty RPN, and we say enter 4180 times 94 times, and what do we get? 1.57 times 10 to the power of 6 joules. Now, what is this? This is the required amount of energy required for the water. Is that how much energy the stove element produces? No. The stove element must produce more energy than 1.5. Why? Because only 70% of the energy that leaves the stove element actually makes it into the water. So, how much energy must the stove element produce? Listen, we need an equation here which dictates efficiency. So we'll say, okay, efficiency is equal to, this is always work out divided by work in. Now, when I say out, I'd like to write the word useful. That really helps me remember how to apply this equation. If I say work useful output divided by work input, this helps me now. You know why? Think about this. You can never have an efficiency over 100%, right? So which one of these two is going to be bigger? The useful output energy or the input energy? Obviously, the input has to be bigger because in order to get 70% efficiency, you're going to lose some of that. So the useful output is going to be smaller. Therefore, if you have a smaller numerator, this is going to be a fraction. It's not going to be greater than 1. It's going to be less than 1, and then we'll multiply by 100, which gives us the percentage efficiency. You see the logic? Let's continue. So how much is what we require? Well, we need useful output of 1.7. Okay? Why do we need useful output? Because that's how much energy the water requires. So if we go back to the picture, the water is going to need 1.57 times 10 to the power of 6 joules. Oops. 6. But the element has to produce more than that because some of it is going away. How much? Well, let's do the equation. Here we go. 1.57 times 10 to the power of 6 divided by W in times 100 equals 70. Easy. Then what you do is you just swap these two guys, right? And you say W in equals 1.57 times, oops, sorry about that. My pen got stuck. Let me erase this for a second. Okay, so that's 1.57 times 10 to the power of 6 joules divided by 70 times 100. Now, what does that give you? I think it gives you 2.24 times 10 to the power of 6. That's equal to W in. Now, and just to check, you can go 1.57, enter 2.24 divided by, and sure enough, that's 70%. Now that we know what the input energy has to be, that's how much energy the stove, that's how much energy we have to pay for. Obviously, okay, we're only using the 1.57 that goes into the water, but we're still paying for everything that comes off of the stove element. Just because it's heating up our kitchen doesn't mean we don't have to pay for it, unfortunately. We still have to pay for it. So how much is that? How much money is that? Think of it this way. 9.5 cents per kilowatt hour. First of all, what the heck is a kilowatt hour? Well, let's rewrite that. 1,000 watts is a kilowatt. And what's a watt? That's 1,000 joules per second. Now we've got a unit of time in there. What's an hour? An hour is how many seconds? Well, 60 times 60. That's 3,600 seconds. Let's cancel the seconds, and when you multiply that out, you get 3.6 times 10 to the power of 6 joules. Or another way of saying that is 3.6 megajoules. So 3.6 megajoules costs 9 pennies. Okay? So how much does how much does this much energy cost? Because that's how much the stove is going to give off, right? In order to figure that out, you say, well, how many times does this go into that? Then all we have to do is multiply by 9, right? But in other words, I could say 3.6 times 10 to the power of 6. How many times does that go into 2.24 times 10 to the power of 6? And I think that is, let's see, 2.24, enter, 3.6 divided by, and we're getting an answer of 0.62. So all we have to do now is say, okay, well, if it was a 1, if it was equal, it would be 9 cents. So definitely it's going to be less than 9 cents, but how much? We just have to multiply 0.62 by 9 cents, and we get an answer of 9 times 5.6 pennies. So that's our final answer. 5.6 pennies to heat up 4 liters of water from 6 degrees to 100 degrees Celsius with a 70% efficiency from the burner to the water. And by the way, we haven't even started cooking our pasta yet. We still, I mean, you don't just bring the water to a boil and say we're done. No, then you put your pasta in the bowl, in the pot, and you still have to cook it for a while. So in fact, my guess is it would probably take around 10 cents to make a meal. But this is a pretty big meal. It could feed quite a few people with 4 liters of water. Hey, thanks for watching this video. See you next time.